So today we're going to introduce the kinematic equations. Now, some of these we've seen before, two of them in fact. It's important to remember that one of the first questions we have to ask is there acceleration? Is the object, whatever it is, changing its velocity? The answer is no if it's a constant velocity. So that might be like if you were on the highway with cruise control. Then you can get away with velocity as distance over time. But much of the time there is acceleration, so we're going to need these kinematic equations. And let's give them a name. Let's give each one a name, because sometimes that helps when referring to them. So the first one is simply definition of acceleration. Velocity final minus velocity initial over the t. Now it's usually really the delta t, the change in time, but most of the time they just give you the t, so we don't have to worry about doing any subtraction there. Now the second one is interesting and very important, because if you notice there's no time in here. It's v final squared minus v initial squared over 2x. This is called the time independent equation. We're going to use it a lot. Now the third one is kind of long, and that's the position equation. You might say, well, I don't want to use that. That's kind of long. I want to try to avoid that one if possible. Well, sometimes it's very helpful, and a lot of times we can make something zero. For example, x initial would be a starting point. Think about it. If somebody's running a race, or a car is starting, whatever, well, set the initial position at 0. It only makes sense. If you have a choice, set everything starting at 0. And if something's starting from rest, well, then v initial will be 0, and that's good too. And then the last one is average velocity. Now, you can't use this like when we're doing those two-part problems, like where you're driving at a certain velocity for a while and then you drive at a different velocity or speed for a while. You can't use this. This is only when you're just doing like a straight acceleration or deceleration. And we'll see that as we go along. So let's take a look at a few example problems. So here's an example problem. An airplane takes off at 27.8 meters per second and can accelerate at 2 meters per second. How long must the runway be so the plane can take off safely? It's always good to do a little drawing. And as you're listening to this, feel free to stop the video and write things down. So in order to take off, the v final, you see, you don't have to draw anything pretty. Even if you can't draw that airplane, just draw a box or something. Is 27.8 meters per second. We know it can accelerate at 2 meters per second squared. And v initial will make that 0. And it only makes sense because planes would be at rest. We're interested in the distance. So that would be the x. Now, up until now, we've had to use definition of acceleration, but we don't know time. And because we don't know the time, we need a different equation. Here's where we're going to use time independent. Whenever we can make something 0, that's very helpful. Luckily, we can make v initial 0. So now, I guess I'll write it down here. Acceleration is v final squared over 2x. We want x. So it's probably not really helpful to have x down in the bottom there. So let's multiply both sides by x. That way it'll cancel on this side. We've got x times a is v final squared over 2. Now I want x by itself, so I'm going to divide by a. By doing the algebra first, we're less likely to make a mistake once we put the numbers in. Because now all we have to do is substitute for the numbers and do the math. And we'll get a runway distance of 193 meters. It's very important when we get these answers to take a look at them and see if they make sense. And you might say, well, how do I know if that makes sense? It's kind of a gut feeling thing, or a personal experience. So 193 meters. Well, a football field is about 100 meters or 100 yards. So this would be roughly 2 football fields. Okay, that's at least possible, maybe for a small plane. And you say, well, how do I know that? Well, what if you got 1.9 meters or 19 meters? That would start to seem too small. So the 193 seems like, okay, yeah, that's probably in the ballpark for a minimum length for a small runway. It's not impossible. We're probably okay with our maths. Now let's take another one. Take a look at a different one here. Again, we'll draw our picture. We have a car. Don't need anything fancy. And let's see what we know. We know that this intersection is 30 meters. We're told I want the car to cross a 30-meter intersection from rest if it accelerates at 2 meters per second squared. Oh, we know the initial velocity is 0. And we know acceleration is 2 meters per second squared. Now, we don't know V final. So maybe we don't want an equation with V final, but it would kind of make sense. Why don't we start x initial at 0 meters? Now, in this case, I'm going to use the position equation. I know it's long. I know sometimes people want to avoid it because it's long, but it's actually going to be easier in this case. All right, so x initial is 0. V initial, the car started from rest, which you would at an intersection, if you're stopped for a stop sign or stoplight, is 0. The position equation is not as scary as it looks, because it collapses down to that. Now, we're interested in how long. We're interested in the time, the t. So let's multiply both sides by 2. All right, we're starting to get t by itself. At least we got rid of the fractions. Now let's divide both sides by a. Let's see. So the a will cancel over here. T squared is 2x over a. Now, don't memorize that equation. We need to know how to do the algebra because that can change from equation to equation. Now, I would say you could take the square root of both sides, but let's not do that just yet. Let's do that at the end. Let's just start to substitute. So 2 times 30, and the acceleration, was also 2. So those 2's will cancel. So t squared is 30. Now we can take a square root of both sides. And the square root of 30 is 5.48 seconds. And that's how long it'll take to go across that big intersection. Now think about how to estimate that in your head. We're trying to get the square root of 30. Well, the square root of 25 is 5. And the square root of 36, because 6 times 6 is 36, is 6. So it really makes sense that the square root of 30 is about 5.5. We can feel very comfortable with that 5.48 second number. Now, we're not going to do the Hot Wheels car today, obviously, because we're not together. But let's take a look at one or two more here. So a pitcher throws a baseball at 44 meters per second. And we're asked, what's the acceleration if it travels through 3.5 meters from the start of the pitch to the release? So obviously the pitcher's arms aren't 3.5 meters, but we've all seen that where they step back and then they step all the way through the pitch. So the ball's traveling quite a distance, and they're doing that to get the ball going really, really fast to throw to the batter. So let's see what we know. We want the speed of the ball, the final speed when it leaves the pitcher's hands, his or her hands, to be 44. Let's assume we start at 0. We don't know the acceleration. But we do know that the pitcher is going to travel, or the ball is going to travel, 3.5 meters. Didn't tell us anything about time, did they? There's no T, and they're not asking for time either. So we can simply use the time independent. Now, one thing to watch out for in the time independent that people forget, and I'm guilty of it too, I've forgotten too, is that it's a squared. Always double check your formulas with your formula sheet, or wherever you're looking them up in a book. Always double check this. And I should also mention some books will write the time independent a little differently. They'll solve it for V final, and that's fine. It's just a different version. I like this version. That's the way I like it written. Now let's see if anything is 0. Yeah, V initial is 0. So get rid of it. You could put the 0 in when you put the numbers in if you like. I like to get rid of all my variables as early as possible. So V final is 44. We're going to square that. 2 times 3.5. And we're going to get a very big number. And I'll double check it with you on the calculator. Divided by 7. Now, you're going to get 276.6 and all those numbers and all that. But with significant figures, it's 280 meters per second squared. Because that only has two significant figures, the 2 and the 8. And the numbers that they gave us all only had two significant figures. All right, let's do one more, and then we'll wrap up. So a dog chases a runner who's running at 1.2 meters per second. So here's our runner. So V initial is 1.2 meters per second. And this person speeds up because they don't want to get bitten by a dog, or they want to get away from the dog, to a certain V final. We don't know what that is. Oh, but let's see what we know. We know the acceleration is 0.8 meters per second squared. And we know the distance is 15 meters. Part A asks us to calculate the final speed of the runner. We don't yet know the time. We will later. So let's see what we can do with the algebra. I use the time independent. Let's get rid of the fraction. Let's multiply both sides by 2x. Whenever we can get rid of a fraction, that's often a good day. All right. Now we want the V final, so let's add V initial squared to both sides, just like we would do in an algebra problem. So V final squared is 2ax plus V initial squared. And I wouldn't solve it for, like, I wouldn't do the square root just yet. I think we'll be all right if we substitute and then take a square root at the end. Now we have to substitute. So v final squared is 2. What was the acceleration? 1.2, no, 0.8, excuse me, 0.8 meters per second squared. And the distance is 15. The initial was 1.2. Don't forget to square it. So we'll put that in our calculator, plus 1.2 squared. And I'll just continue up here. V final squared is 25.44. So if we take a square root of both sides, well, square root of 25 is 5, so I absolutely believe that 5.4 meters per second. That's going to be our runner's final speed when they accelerate. B says, well, how long did this take? Probably the easiest way is to use simply definition of acceleration. And make sure you don't square it there. You see, I forgot and started right the squared in. But I caught myself. I double checked it. All right, now I'm running a little bit low on space here, so I'll write it up here. Acceleration is v final minus v initial over t. We're interested in t. So let's multiply both sides by t. So time times acceleration is v final minus v initial. Divide by a. We can't make anything 0 because he didn't stop at, or he or she didn't start at rest, start from rest, or stop it at the end. We have a v final. We had a v initial. We had an acceleration. So when we do all this math, we get 4.8 seconds. So now that I have a clean slide, let's do part C. Calculate the average speed. So to calculate the average speed, we're going to use the average speed formula. V final plus V initial all over 2. And note that it's plus here. And this one's pretty easy because we just have to substitute. We can almost do this one in our head. 5.04 plus 1.2. Well, that's 6.24. All over 2. So that's 3.12 meters per second. So that's the average speed. Now, they didn't run that the whole time. They were accelerating in the process. We're saying on average, that's what they ran.